Okay, now today we will go to the third lecture in the series. In the first two lectures we have talked about the basic marine hydrodynamics, its introduction, motivation. In the second lecture we have talked about basically the continuity equation, and while talking about the continuity equation we talk about vorticity vector, then irrotational motion, and from that we could get that existence of a velocity potential phi which exists in case of a rotational motion in a fluid flow problem. And today again now we will go to what about the flow direction, in which direction how to know the direction of the fluid flow. So, in this context we will talk about streamlines and path lines. Streamlines. For a fixed instant of time, let us draw a curve in the fluid, a space curve. At a particular point, let us draw a tangent to this, and if a q bar velocity vector, if a velocity vector q bar is same as the direction of the tangent, that means q bar cross dr bar equal to 0, and then this line, this curve we call the streamline, because that means along a streamline the flow, it gives the direction of the flow of the fluid, and then as a result there is no fluid usually across a streamline, there will be no flow. No fluid will pass through the streamline, it will always gives the direction of the flow. So, if you simplify this one, then you have dr bar is equal to dx I hat dy j hat, these are the components, dz k hat. Then we have already q bar is equal to u I hat plus v j hat plus w k hat. From q dot dr bar is 0, this will give us I j k, we have u v w, you have dx dy dz, and if this is 0, because this is what your q bar cross dr bar gives, and if this is 0, then it gives us from this you have u dz, rather if I go to this, then v dz minus w dy is 0, then you have j, then you have u dz, that is u dz minus w dx is 0, and then we have, if you k component, you will have u dy minus v dx is 0. From this we can easily get dy by v is dz by w, and from here we will get dx by u is equal to dy dw by, sorry, this is called dz by w, and then you have from here we will get, from the third one we will get dx by u equal to dy by v. So, if you combine the three things, we will get dx by u dy by v is equal to dz by w. So, this is what we call the equation of the streamline. So, we can take any two of them and solve it, and so that will give us two sets of constant. If I said that I will take either any two, either these two I can take, I will get two sets of equations, and I can take these two, or I can just take one and third. So, that will give you often. So, because of that we say that it gives two infinity set of constants, and this is the equation of the streamline. Now, let me just take a simple example to understand what exactly how it means. So, if I say I will take a simple example, like if I say my velocity vector q bar x I hat minus j y j hat. If this is the velocity vector, then what will happen to my streamlines? Equation of the streamline will be dx by x will be dy by minus y. Once this gives me, so it gives me ln x minus ln y plus constant, which gives me ln x y is equal to constant, and which gives me x y is equal to constant. And since if x y is constant, then what will happen if I draw these lines? So, this is for each constant, suppose we will call it k, and this constant since it is, so what will happen then? What if I draw these lines? Let me see in the xy plane, this is x axis, this is my y axis, and if I draw it, this will give me curves like this for various values of constant. And again, because similarly we can get in the, now I will go to, this is one example. For x positive, y positive, we can get when k is constant or k is equal to 1, 2, 3, it can have any values, and also, so we can have, this is one of the example. So, now some of the points to be noted, note. So, in case of a streamline, streamline flow, the flow direction of flow is in one direction. Is in one direction. As I have already mentioned, there is no flow across it, there is no flow across a streamline, across the streamline. And as I mentioned, the differential equation of the equation of the streamline is double infinity of solution. And in this case, we have this q bar is x I hat, this is a two dimensional flow, this is the one. Now, once we know what is a streamline, what will happen, like in case of a vortex lines, we have got a vortex tube. What will happen if we take up any closed curve? If you think of any closed curve and draw a streamline, in the inside the fluid you have a closed curve, let it curve gamma. Like in case of a vortex lines, vortex tubes, we have seen that we taken any closed curve inside the fluid and we have drawn vortex lines, we got a vortex tube. Similarly, suppose I say I have any closed curve, and at each point of the curve, if I draw a line, draw a streamline, then this will give me a tube, and this tube I call this as a stream tube. And Now, let us look at the flow in a stream tube. If I look at the flow in a stream tube, then let us say that let us look at a stream tube of various cross section. This is cross section A1, this side is A2. Let this B3 is the boundary of the tube, and then these are the two cross sections. So, there are three, one is A1, A2 and A3. So, let us say that fluid is flowing along this direction and it is going out in this direction. Now, let me say that at this point, if n hat is the normal, unit normal outer drawn direction, and here also we have a outer drawn direction normal n hat. Okay. So, if that is the case, and we assume that the fluid is entering through the cross section A1 and it is going out through the cross section A2, because it is and there is a, now what will happen if we will say from the continuity equation we have for a incompressible fluid we have the this is equal to 0. We have seen in case of continuity equation. If this is the case, then which is same as integral over the surface q bar dot n hat ds, that is 0. Now, if I look at the cross section, now this surface has, we have three surfaces, we have A1, we have A1, A2 and A3. Since we have three surfaces, since we have a streamline flow, this is a stream tube and there is no flow which will cross through A3. So, because of that we will have integral over, this is called the surface S1, this is my surface S2, this is my surface S3. So, there is no flow across S3. So, what will happen, my this will be same as integral over S1 q bar dot n hat ds plus integral over S2 q bar dot n hat ds will be 0, because there is no flow which is crossing the surface S3. And if that is the case, then because we have one is the inward direction, because this side you have the stream tube, this side your flow is entering, this is the way flow is entering and this is the flow. So, outer direction is both. So, we can have this is the outer direction, here it is the outer normal. So, if then in that case, so we will have integral over S1, that means A1 Q1 dot n hat dA1 plus integral over A2 Q2 dot n hat dA2, this is 0, and which implies Q1 A1, because the normals are in the opposite direction. So, you will have a negative sign. So, that will give Q1 A1 is Q2 A2, and this is what in case of a stream tube, the amount of fluid that will enter through this, and in that same amount of fluid will go out through this. So, now if I say A1 is A2, which implies from this relation we will have Q1 is Q2. That means, when we have a tube, stream tube of uniform cross section, the speed remains the same. Now, to demonstrate this, let me take an example. Let us consider a stream tube, a circular pipe. So, this is a tube, it has fluid will enter through this one and it will exist this way, it will enter this way, it will fluid will leaves. Let this point be A, B, C and D. If I say my diameter dA is 6 inch here and here dB, the diameter at the point B is equal to, I will say 12 inch. At C I will say this is 4 inch, DC that is 4 inch and diameter at this point DD, this is I will say 2 inch. So, it is clear here this is diameter is 6 inch, here the diameter is 12 inch, from there is a bifurcation and here diameter at point C it is a 4 inch and here it is 2 inch. Now, if I say the velocity, the fluid velocity at B is 2 feet per second. If it is at 2 feet per second and again velocity at C, let me say this is 9 feet per second. My question is, find the fluid velocity at A and D. That means, at which rate the fluid will be entering through this tube and at which rate the fluid will be going out through the D tube, through the face D. Now, since we have seen that in case of a stream tube, we have seen that the Q1 A1, so QA, DA, QA, rather I will call this as S1 is QB, SP. S1, S2 are the surface area and this is a cylinder here. So, my QA into S1 is pi into d square by 4, 36, this is 36 by 4 and this is QB. QB here it is 144 into pi by 4 into QB at this point is 2 feet 2, which gives me my pi will cancel 4, then I have QA will be, if I cut this with this, then it will be 4. So, 4 into 2 is equal to 8. So, QA is 8 feet per second. Okay. So, my speed at here becomes 8 feet per second. Now, in the same way, what I will do that I will, because I know this speed here, I have the fluid speed. If I say that at QB, at this will be QB, SB will be same as QC my SC plus my QD SD, and if I utilize this, substitute for this, then I will easily get, I am not going to the detail, I can get my QD as 36 feet per second. This is what I will get. It can easily check that. Just a simple calculation I am leaving it to you. So, these two examples suggest that how the fluid flows inside a tube of certain cross section. If the cross sectional area changes, then the velocity of fluid changes, fluid velocity changes. And here that is why sometimes when we have a very the flow through a nozzle, the speed becomes very high. It is because that the nozzle, the area we squeeze the area, and in the process the speed of the flow speed will be high, fluid will flow at a higher rate, the speed will be high. Now, with this I will go to what is path lines, particularly path of a particle. Basically what we talk about here, the path of a particle. The path of a particle is a curve, again it is a curve, the path of a particle is a curve which a particular fluid will describe during its motion. So, the differential equation of the path line will be dr by dt, because this will represent the fluid motion. So, dr by dt will give you q bar, and what is q bar? Q bar is u I hat plus v j hat plus w k hat. So, that means, and if I put it in r as, I write it for r as x I hat plus y j hat plus z k hat, then we have dx by dt equal to u, dy by dt that is equal to v, and dz by dt that is w. These are the equation of the path lines. Now, the question comes, we have already seen that how far the path lines and streamlines are different, basic difference between path lines and streamlines. So, the tangent to streamlines, we know that the tangent, if we draw a tangent to the streamline, it gives us the direction of velocity tangent to a streamline. If we draw a tangent to a streamline, it gives us the fluid particle, it gives us the velocity of the fluid particle basically the fluid particle at various point. On the other hand, the tangent to a path line, if you draw a tangent to a path line, gives the directional velocity, it gives the velocity, directional velocity of a given particle at various time. So, basic difference is that here it gives the when we draw a tangent to the streamline, it gives us the velocity of the particle at various points at the same instant of time. On the other hand, if we draw tangent to a path line, direction of the velocity of a given particle, this is the difference at various times. Here various points, here at various times, here the given particle of a particular particle at various points, whereas in case of streamlines it gives the same particle at various points. basically here time is fixed, and in this case here time is varying, space is position is fixed. On the other hand, if I will say that when the motion is steady, if the motion is steady, then streamline do not vary with the time and it coincides with the path lines. Now, with this background of streamlines and path line, I will just go to two dimensional flow. Why the need of two dimensional flow? Because everything in nature is three dimensional. Why should we think of a two dimensional flow? When it comes to particularly, we have the three components of velocity u, v, w. Suppose one of the component is very small or negligible. So, in such a situation, what we will do, then we can consider, if one of the component is small, then we can consider the flow as two dimensional. And in fact, it has been found that in many situations, when the flow is symmetric along a particular direction, then it is easy to analyze, consider the flow as two dimensional. And from experiments and observations, it has been seen that while physical modeling, in many situations the two dimensional flow gives a very accurate realization of the flow situation. Even if there are axisymmetric flows, here the flow is considered as a two dimensional flow. So, because of that, there are two aspects. One is either the certain symmetric characteristics of the flow, if certain symmetric characteristics of the flow is there, or when the one of the component of the velocity is negligible, then we can always consider the flow as two dimensional, and that gives a very good accurate realization of the flow characteristics. Because suppose if we consider one cross section, particularly what happens in the large ocean when you deal with large problems related to ocean waves, are often we consider the flow as, if the flow characteristics is similar in each section, each cross section, particular cross section, we always consider the flow symmetric, assuming the symmetric characteristics of the flow, we always consider the flow as two dimensional. So, it has been seen in many cases that this gives a very good realization, particularly for large class of marine hydrodynamics problems, and it is easy because the moment you reduce the dimension by 1, the complexity of the problem reduces, and that helps us to understand get a very accurate realization of the situation in a very simplified manner. Often we try with a two dimensional problem, once we get a proper feeling about the problem, then we go to the general case, that is what we do. Now, with this I will now go to few problems related to the two dimensional flow problems. Particularly we have already talked about the what will happen to the continuity equation in two dimension. Continuity equation, particularly here I want to say emphasize the when the flow is incompressible, because as I have mentioned earlier that here we will be considering for a large section of this course as the basically marine hydrodynamics we concentrate on incompressible fluid, and for for incompressible fluid, if the two dimensional continuity equation will be del u by del x plus del v by del y 0, this is the continuity equation. And now let us consider the differential, because and then we have the streamlines, we have come across the streamlines, that is the equation of the streamlines are dx by u is dy by v. This will give us the streamlines for a two dimensional flow. If that is the case, then what will happen? Let us consider the differential u du v dx minus u dy. If this, consider this as 0, if this is 0, that gives us, from this we can always get this v dx minus u dy 0. If v dx minus u dy is an exact differential d psi, then what will happen? So, that will be 0, then psi is a constant, and that psi, because this psi is equal to constant, again what will happen? If I relate with, so further we can see d psi as del psi by del x, because if psi is a function of x y, if I say psi is a function of x and y, then d psi will del psi by dx plus del psi by del y dy, and this is same as v dx minus u dy. So, if you compare this component wise, we will just compare the x part, dx part and dy part, then you can say del psi by del x is equal to v, whereas u is minus del psi by del y. So, in fact, this psi is called the stream function, psi is equal to constant, psi is the stream function, this psi is called the stream function, and psi is equal to constant, as we have seen that they will give the streamlines, that will give the streamlines. Another point of view here, now I will relate phi with the stream function with the velocity potential. We have already seen, in case of a two dimensional flow, we have already seen u is equal to phi x, v is equal to phi y. Now, from here again, if you relate with the stream function, so we have u is equal to phi x, and phi x is nothing but, we have u is nothing but minus del psi by del y minus psi y. Similarly, if we say v, that is your phi y, and v is again del psi by del x. So, which gives us del phi by del x is equal to minus del psi by del y, and again del phi by del y is del psi by del x. This is the, sometimes in complex function theory, this is the Cauchy-Riemann equation. Particularly if f is a function of a complex variable z, that is given as phi x y plus I psi x y, then f is analytic, we say f is analytic in z provided if it satisfy the Cauchy-Riemann equation. So, this is the Cauchy-Riemann equation, in short we call it Cauchy-Riemann equation. So, that means for a two dimensional flow we will have, if the flow is potential. So, here it is very clear, that means I have already mentioned that the streamlines exist for all flow, exist for all flow. On the other hand, we have velocity potential will exist only when the flow is irrotational. It will exist for irrotational flow. On the other hand, for streamlines, they are only for two dimensional flow. Streamlines, they are associated with two dimensional flow, and the flow is two dimensional. On the other hand, when it comes to the streamlines, particularly I will say rather stream function, this is not streamline, stream function exist for all flow, whereas this is again stream function. exist for two dimensional, whereas velocity potentials here both two, it exists for both two or three dimensional flow. So, this is this is a very clear difference between what I say the streamlines, stream function and velocity potential. Now, another thing here, that what is the another basic difference. Now, let us just say that if I say phi, what will happen to phi x psi x plus phi y psi y? This will give phi x is u, we have seen phi x is u, and psi x we have seen it is v, whereas phi y is v. We have seen psi y is minus u. So, this is same as u v minus u v, that is equal to 0. So, which I can always say that grad phi dot grad psi is nothing but grad phi, this is 0, which implies that the streamlines, because phi is equal to constant gives the streamline, psi is equal to constant gives the phi is equal to constant it gives us the equipotentials I have already mentioned, whereas the psi is equal to constant gives the streamline, it gives the streamlines. So, this suggests me that the streamlines and the equipotential lines quote orthogonally. This is another. So, this is another very important result. Here another point I would like to highlight, that I have already mentioned, that the velocity stream function is independent of the fact whether the flow is rotational or not. On the other hand, the velocity potential phi, they exist only for irrotational, when the flow is irrotational, and that is of potential kind. So, irrotational flows are often called as the potential flow. Now, I will come to couple of examples rather, to understand that how the flow characteristics are defined in case of various examples. The few examples rather I will concentrate on to understand the path lines, streamlines, then irrotational flow, stream functions, and how they are related. So, to do that I will go to this one by one, let us work out few examples. And so, here I will 4-5 examples, let us work out. Let me say q bar equal to k square x j hat minus y I hat divided by x square plus y square. Here I assume k is a constant. So, now whether this q bar represents whether it has it relates with some fluid motion or not, then if so, if a motion is possible, fluid flow is possible, find the streamlines. And then that is the first part. Second part, test whether the flow is irrotational, test for irrotational motion. Again If the flow is rotational, then find the velocity potential. So, here I have for this given the velocity vector, I have two questions. First question I am emphasizing whether to test whether the flow is possible, fluid flow is possible or not. Once we say that the fluid flow is possible, then we will find that what is the streamline, because that will give us a direction of the flow, and then we will check it for whether the flow is rotational. If the flow is rotational, then we will find the corresponding velocity potential. So, here we will find the streamlines, we will find the velocity potential, at the end we will check whether they cut orthogonally or not. That is what we will do. Then it will clarify some of our whatever we have theoretically discussed. Let us check for it. First, this is a two dimensional flow, and for a two dimensional flow we have divergent of q bar is 0, that is del v by del x plus del v by del y is 0. This we have to check because it is two dimensional. And if we will show del u by del x, what will happen here? Here your u is minus k square y by x square plus y square, and your v is k square, that is x by x square plus y square, and then what will happen here, which implies del dot q bar will be k square into minus del by del x y by x square plus y square plus del by del y into this is x by x square plus y square, and this gives us k square, and if you take the derivative with this is minus 2 x y by x square plus y square square, this will give you plus 2 x y divided by x square plus y square square, and that gives us 0. Hence, fluid motion is possible. In compressible fluid, we have a possible fluid motion. Motion is possible, and once the fluid motion is possible, now whether we say that what will be the streamlines. Now check for rotationality. Let us see first whether the flow is rotational. If it is rotational, we have to check it for curl of q bar is 0. Curl of q bar is 0 because for a rotational, and that is same as because the flow is two dimensional here, we have to check it as if del u by del y is equal to del v by del x. This we have to check. And here you can see that easily here del u by del y minus del v by del x, this is equal to y square minus x square del u by del y. This will give you y square minus x k square into by x square plus y square square, then plus x square minus y square divided by check it, and that gives us 0. Since this is 0, so the flow is rotational. So this is satisfied, and we have already seen this satisfies this divergent q of 0, fluid motion is possible, and here we are seeing flow is rotational. So now we will go for what are the streamlines and what are the velocity potential. To find the streamlines, what we will do? We have the streamlines will give us equation of the streamlines is dx by u is dy by v, and that gives us, because we are dealing with a two dimensional flow, so that will give us dx by minus y, because it is y by x square, and that will give you dy by x, which gives us x square plus y square is equal to constant. So, this gives the streamlines. So, it is concentric circles. This is all will give us concentric circles. On the other hand, if you look at the velocity potential, so in that case we will have u is equal to phi x and v is equal to phi y. Already we know u v. So, we have phi x is equal to k square y by x square plus y square, and phi y minus k square x by x square plus y square. So, if you integrate it, then we get phi from this one, we can get phi is equal to k square y integral dx by x square plus y square, and that gives us k square, and I get a tan inverse x by y tan inverse x by y plus f of y. Now, what will happen to if I take del phi by del y of this? This gives me k square del phi by del y. If I go for del phi by del y minus k square x by x square plus y square plus f dash y, and this is same as already I have been given phi y is this minus k square x by x square plus y square. So, which implies, because this implies f dash y is 0, because this term will get cancelled with this term, then we have f dash y is 0, and that means f y is constant, and this constant we can always say equal to 0 without loss of generality, because a constant we can always take it as 0. So, we have taken it as arbitrary constant, so we can take it as 0. That gives us, which gives, so phi we get it, phi x y we have got it as k square tan inverse x by y. Now, if I say that phi x y is constant, will give me the equipotential lines. If I put this as constant, which gives me x is equal to c y. So, if these are the concentric streamlines, now x is equal to c y is just draw a line. If x is equal to c y, then what will happen? They will just pass through the origin. Any line will pass through the origin. Sorry, it will go through this origin, and you can have number of lines, and this is a line passing through the origin. These are all circles. So, if you look at draw at any point a tangent, you will see that these two lines, the streamlines and the equipotentials, they will cut each other orthogonally. So, this is what it shows. The another point is that here we have seen the flow, the streamlines they are circles, whereas the flow is rotational. The streamlines are circles, they follow a circular path, the fluid follows a circular path, whereas the flow is rotational. Now, I will show you in another example that the flow is rotational, they are circular as well as the flow is rotational in nature, they are not irrotational. Let us look at this example. Suppose my q bar is minus w by W x 0, let us say omega y, then we can see easily that del dot q bar is 0, and again so which shows that flow is incompressible fluid flow is incompressible, that means there is a fluid motion is possible. And if you look at curl of q is 0, which is same as, which implies I j k, if you take del by del x, del by del y, del by del z, and then u is minus omega y, omega x, this is 0, and this you calculate, you get it 2 omega k hat, and which is not equal to 0. So, curl of q, sorry, it is not 0 for a rotational flow. This is for a rotational flow, where I am finding here curl of q is not 0, hence this flow is not rotational. Now look at what is the streamlines. If you look at the streamlines, you have dx by minus y is dy by x, and again which gives you x square plus y square is equal to constant. So, if this is the streamline, for each constant you have a circle passing through origin and center is at origin. On the other hand, here the curl is not 0. So, that means we have a fluid flow where the fluid particle follow a circular path, whereas the flow can be remain rotational. Whereas in the previous example we have shown that the flow can be irrotational, but still the fluid can follow a circular path. With this I will stop today. Thank you all.